Yeah, thank you very much for the nice introduction. So my name is Josef Domitner. I'm with the Graz University of Technology. First of all, I would like to thank my co-authors, especially Amir, who prepared the presentation and who gave the input for this presentation. So just a few words to our research group. So we are mainly mechanical engineers. So we are working on macro scale problems. And so also this presentation deals more or less with the macro scale problem, which is a little bit different to the presentations we saw before. To the content of my talk, first I will give the introduction, why we did this work. Then I will describe the methodology, including the materials we used, the simulations and the experiments we performed. And at the end, I will describe the results and the conclusions. Some of you perhaps know that the investigation of hydrogen cracking is standardized, yeah? And there are some investigation methods according to the ISO 11114. These methods can be distinguished. These methods are disk testing methods, then load-controlled fracture mechanics methods, and displacement-controlled fracture mechanics methods. So this means here, for example, you apply a defined load until fracture occurs, and then you investigate the behavior of the sample under hydrogen atmosphere. Here you apply a constant displacement, and then after a certain time in a hydrogen atmosphere, for example, inside of an autoclave, you investigate the fracture surface, and then you can also see if the crack grow or not. And with this, you can then characterize the susceptibility of the material to hydrogen. We are normally working on this method. So we use samples where we apply a constant load, put these samples into the autoclave, apply a gas pressure, and after a certain time, we investigate then if a crack grow happened or not. If we stay with the displacement controlled method, we have normally three types of samples which are proposed to use. So this is this sample with a screw, this cantilever beam with 2 screws, and here such a cantilever where we insert a wedge to spread up both sides, and then to introduce here a certain displacement that the crack growth can happen. The problem is now, especially if you have an autoclave which has a limited volume, that these kind of samples, even if they are only about 70 or 100 millimeters long, are big, because if you would like to do a testing of different materials, for example, or if you would like to do testing of many materials in parallel, you need to place as much samples as possible inside of the autoclave, because such an autoclave charging cycle takes at least, I would say, 3 weeks, and most of the cycles takes up to 6 weeks. So this means within the 6 weeks, you are not able to use the autoclave. Therefore, you have to put as lot of samples inside as possible. And therefore, our idea was, even if these samples are not that big, to use even smaller samples, which are also standardized. Yeah, these are the so-called compact tension samples, but these are standardized for load control methods and not for displacement control methods. The advantage of these small samples is that they have a very compact geometry. The manufacturing is much easier. For example, here you do not need any threads, as for example here, and any of you perhaps know, if you are investigating some Inconel alloys, for example, how difficult it is to get the thread inside of such a material. Yeah? So this means the manufacturing here is easier. And for applying the load, for measuring the displacement, you do not need a clip gauge with this method. The problem here is only that if you insert a wedge in such a small sample, you do not know what's the exact contact force here, because you also generate here some plastic deformation at the contact surface. And the actual contact force is necessary to calculate the stress intensity at the crack tip, which you need. Therefore, for example, here, if you use the big sample, you have this lift-off curve, and where we have this edge in this lift-off curve, you know this is the contact force. For the smaller sample, it's not that easy. As I said, you introduce plastic deformation, the loads are much higher here. So the question is, what should you do? And what are mechanical engineers always doing? They calculate the correction factor. And we did this using finite element simulation. So for such a sample geometry, we calculated a correction factor to account for these, let's say, difficult contact conditions. And with this correction factor, we were then doing our tests and calculating the stress intensity. I will show this now. Which material did we use? So we used a high-strength steel. This is a tool steel, which is hardened and annealed. You see the yield strength of this steel is about 1.3 gigapascal, and the tensile strength is a little higher. The question is why we use such a high-strength material, because for such materials, you see the influence of hydrogen very well. Yeah? You can also use here for the same tests some standard pipeline steels, but then you will never see any influence. We also calculated the fracture toughness using such samples. So the fracture toughness without hydrogen, so at ambient air, it's about 125 megapascal square root meter. Here I have to add the information that this sample is comparatively thin. Yeah? So normally, if you do this testing, you use samples which are quite wide to ensure that you have at the center a plane strain condition. But this cannot be fulfilled every time. Yeah? For example, if you would like to investigate pipelines, then you are limited with the thickness. Many pipelines are just about 8 millimeters, 10 millimeters, 50 millimeters in such a range. Yeah? And therefore, you have samples which are comparatively small. Therefore, this is the so-called KIQ value and not the KIC value, not the fracture toughness of the material. Okay? But anyway, this is how we have a problem we have to live with, because we cannot choose which material we are investigating. Yeah? The simulation model we set up. So here you see this two-dimensional model. So we simulated two steps. In the first step, this wedge is inserted to apply here the displacement. And in this step, we are able to calculate the contact force between the wedge and the sample and the equivalent force. Why equivalent force? Because here you have, as I said, plastic deformation. So this means the contact force is not in this loading direction, which is at the center of this hole. Therefore, we have to calculate an equivalent force, which reduces the contact force to this center line. Moreover, after the first step, you can calculate the stress intensity factor here at the crack tip. And in the second step, we open then this wedge. And with the opening, you can then determine what's the lift-off force. And the ratio between the lift-off force, or the ratio between the equivalent force and the lift-off force gives you then this correction factor. If you would use a standardized sample, so the bigger one, as I said before, those forces would be almost equal. But in this case, with this compact sample, it's not the case. And therefore, we need this correction factor. Then, to verify if our method works or not, we produced the samples, as you see here. And these samples are normally wire cut. And at the crack tip here, at the notch tip, a crack is inserted. And how you do this? You apply fatigue loading. And this fatigue loading introduces then this crack. Also, the crack length is standardized. So you have to refer to a standard for this. We produced this kind of samples, which are our small samples, out of standard. But as I said, they are very compact. And we produce standardized samples to compare both sample types, the results of both sample types. Why? Because the results of this sample should be identical to the results we get from the standardized sample. Yeah? What's important is that this stress intensity at the crack tip of both samples is equal. Yeah? So to get here the equal stress intensity, we did the finite element simulation of this sample where we adjusted the displacement or determined the displacement which is necessary to get the same stress intensity for both samples. Then now comes the interesting thing. We put both sample types into the autoclave. So as I said before, the volume of such autoclaves is limited. Why? Of course, we have autoclaves which are much bigger. But the problem is the bigger the autoclave, the higher the pressure, the higher the temperature, the more difficult it is to get a permission for such an autoclave. Therefore, in our case, we have this small one. It has about a diameter of less than 100 millimeters and also height of about 120 millimeters. And what you see here, also interesting, so such a small autoclave allows to increase the temperature. So in our case, we can go to pressures up to 500 bars, for example, and to temperatures of about 500 degrees. So these are really conditions which, which are similar to industrial applications. And I have to say the charging in gas atmosphere is completely different to the charging in electrochemical charging, for example, as many or as most are doing, but I think you know this. Here again, important two specimen types, but the stress intensity was the same. The charging conditions in this case, so we used pure hydrogen gas, we charged at room temperature, had a pressure of 200 bars, and as I said, such as charging time typically is between 3 weeks and 6 weeks, yeah, so very long. Now to the results. What you see here is the stress intensity factor at the crack tip. So we use 7 different stress intensities, so from 90 megapascal square root meter to 14. You see here, some of these numbers are red. So this means these samples cracked. I will show it later, and these samples did not show a crack. And depending on the contact force, on the offset of this contact force from this load line, and on the lift-off force, which was determined, we calculated this correction factor for each of these samples. What you see here now is the different cracking depending on the stress intensity that was applied for both sample types. And as you see, this non-standard sample, as we use them, showed the same cracking tendency than the standardized sample. And if you look in detail, then you see that at high stress intensities, you see this kind of branching of the crack for both sample geometries. Yeah? Whereas if the stress intensity decreases, the crack only grows linear. So why this happens? We think this is because of this typical butterfly shape of the stress zone. So here at the crack tip, you typically form this butterfly-shaped stress zone. This means in the direction of 45 degrees, you have the highest plastic deformation. And as you know, there where plastic deformation is, there the hydrogen goes in, and the hydrogen is accumulated. And therefore, it seems that this branching happens because the hydrogen goes to the zone of plastic deformation. There, it accumulates and decreases the crack growth resistivity.
2 minutes.
Therefore, this difference in the crack shape. And what you see here is that no crack grew because the stress intensity was too low. So this was just a pre-crack, which we introduced before. Now, at identical stress intensity and hydrogen gas charging conditions, you see that both samples are equivalent with our method. And especially for this steel, what we saw is that this fracture toughness decreased from 125 megapascal square root meter to somewhere between 28 and 40 megapascal square root meter. So this means you have here a decrease of 2/3 or 3/4, depending. So strong reduction. of the fracture toughness. To conclude my talk, the advantages of this simple geometry is that it's very compact, so you can put in more samples than with such a geometry, for example. The manufacturing is much more simple, and the loading is easier because you don't only have to put the wedge inside. We successfully applied this to investigate hydrogen cracking. We used a simulation to calculate a correction factor to account for this plastic deformation here at the wedge. And as demonstrated for high-strength steel, we showed that you have really a strong decrease in the fracture toughness, but both samples deliver the same results, more or less. So to come back to your talk, so we also like to destroy such samples as materials, but we don't like to clean up the mess afterwards. So perhaps we can then share the work later. Okay, thank you very much. If there are any questions, you're welcome.